Hi, good to have you here. Let's break this problem down in a way that makes sense. Today, we are looking at problem number 77, combinations. The problem statement given to us is that we are given two integers n and k, and we are to return all possible combinations of k numbers chosen from the range 1 to n. We can return the answer in any order. Let's look at this with race framework. We start with reasoning with the question. Let's look at the example where n is given as 4 and k is given as 2, which means we have to return all possible combinations of k numbers chosen from the range, which means we have two slots to fill if k is 2, and the candidates that we can fill it with is numbers from 1 to n, which is 1 to 4. The output for this looks like this, where the first three elements have 1 in the first element, the second two has 2, and the third one and third set has 3 and 4. And if you just focus on this again, I goes from 1 then to 2 and 3, and within each set the other element goes 2, 3 and 4. In other words, we can also visualize this as the first element be as I, which chooses its value from 1 to n minus 1. So in this case, it's 1, 2, 3. And j chooses its value from I plus 1. So if you see, if I is 1, j is 2, which is I plus 1. So j chooses its value from I plus 1 all the way up to 4. And so this can be solved with a for loop where I goes from 1 to n minus 1 and j goes from I plus 1 to n. If we now think about the complexity, it will be O of n square. And please keep in mind it's square, so the power is 2 here because k is 2, which means if k becomes 3, the complexity will become n to the power 3. Generalizing, the complexity actually is not n square, it's actually n to the power k, which means it is exponential to what k is given. Therefore, this is a rather rudimentary approach. It is a brute force where the complexity is n to the power k. Before moving on, let's reason a bit more, looking at our answer set. So for our answer set given n4 and k2, observe that because 1, 2 is a part of solution, 2, 1 is not, which means that if we use 1 for the second slot, you can use 2, but when you place 2 in the first slot, 1 is not allowed. And that's because this is a combination. Order does not matter. 1, 2, 2, 1 is still the same combination. Let's write that down. Order does not matter. Furthermore, we want to make sure that we do better than n to the power k. So let's note that as well. We have to do better than O n to the power k. With those observations, now we are ready to look at the approach, which is better than our exponential n to the power k. So let's say we have two slots, which is k2 and n4, which can also be translated as candidates 1, 2, 3, and 4. So for the first slot, we have the following candidates 1, 2, 3, and 4, right? Once you've used up 1, you can further use 2, 3, and 4 for the second slot. So this is our first slot selection, and then this second level of the tree is our second slot selection, right? Moving on, if you've used up 2, now we know that we cannot use 1 again because we already know that order does not matter for the answer. 1, 2, 2, 1 are the same combinations. So if you use 2 in the first slot, the only choices we have is 3 or 4. And if you use 3, similarly, you have only 4 because 4, 3 and 3, 4 are the same combinations. And if you use 4 in the first slot, then second slot really does not have any candidates, so this will be empty. So if we gather our answers, from here we get 1 and 2, here we get 1 and 3, 1 and 4, 2 and 3, 2 and 4, 3 and 4, and this becomes our solution set. So this is our approach 1. To summarize, I've cleaned up the tree a little bit. So you start with 2 slots. Each level represents 1 slot. So this level here is slot 1 and this is slot 2. The way we work through this is, for the first slot, we have all the 4 candidates. Once you've used up 1 for the first slot, for the second slot, you either have 2, 3 or 4, which gives us the answer 1 and 2, 1 and 3, 1 and 4, and so on and so forth. We can now take a look at the code. So let's say we have a function called combo. The first parameter that we have is candidates. Second will be our, not n, we'll have k, which is the number of slots. And let's have a current. So this current is the variable which will hold all the intermediary results. Okay, so now if you think about this, the first slot can be any of the candidates. It'll work in a recursive fashion, but it helps if you can see the tree in the breadth fashion as well. So for the very first level, as you can see, it is a for loop and it'll range over the length of candidates and it'll call itself. And okay, so now the candidates, if you can see, for the very first time it'll be all the candidates, which we are already doing. But for the second turn, we'll have to exclude the first element and send the rest. So once 1 is included, we'll only send 2, 3 and 4. And that in Python can be beautifully done by slicing. So here you'll say candidates I plus 1, 2. And if you just leave the second open, it means up till the end. K remains as it is. And current is an array which will take our ith element. So we just appended 1 in our answer. Okay. We also have to add a terminal condition. So what will the terminal condition be? As soon as our current, if the length of current becomes equal to k, which means all our slots have been filled, that is where we return. So we just say if k equals to length of current, we return. So this becomes our terminal condition. This is our core logic. So if you try and populate some of the nodes, here on the very first element, our call will look like something this. Our call will look like combo candidates. So since we have removed element 1 here, so here we removed 1, which means it'll have only elements 2, 3 and 4. K will remain 2 and current will become 1, exactly what we wanted. In the second call, similarly, for element 2, it'll become 3 and 4 and k is 2, and this will become 1 and 2. After this, after the element 2, our current is of length 2. So here our current, which is 1 and 2, so the length of current will become 2 and k is also 2. So this is where our terminal condition will hit. And it will return. So as you can see, we made a small mistake here. Here we also have to capture the result. So if there is a global variable, let's say answer, we just append current to answer and then we return. So this step is sort of important because we have to collect our answer. So in this case, 1 and 2 will get collected in the answer and the tree will keep going. For the second case, after 1 has been added to our intermediary answer, I will get incremented from 2 to 3. 3 will get added into the answer here. So a similar call like this will be created where 1 and 3 will be added, k will remain 2, and our intermediary result, the intermediary result here will be 1 and 3, and the candidates that will be left will only be 4. So if I quickly write that down, it will look like something like this. The candidates that we have will be 4, k will be 2, and this is our intermediary result. So this is what our intermediary state will be. If you keep going, again the terminal condition will hit because the length of our current has become equal to 2, and this is where the answer will get collected in our global variable and will return. I hope this is clear. This was approach 1. We'll look at another approach now, approach 2. This is another pattern which is used in these recursion / backtracking problems a lot. Let's start with our example N4 and K2. We again have 2 slots, and the candidates that we have are 1, 2, 3, 4. As opposed to saying that we have 4 choices, like our n's, for each slot, now we just make a binary choice for element at position 0. So here, each level will be choice for element I. So here in this case, it will be for element 0, which is 1. We'll make the choice if we want to include A or not. So for 1, our intermediary result will consist of 1. And for our second node of the subtree, our intermediary result will not consist of 1. We make a similar choice for 2. So either we add 2 or we do not add 2. Here also we do exactly the same thing. Either we add 2 to our answer or we don't add 2. We do the same with 3. But notice, when we start doing with 3, this sort of becomes our intermediary answer becomes equal to k. So this is where our terminal will hit and we return. But we'll continue on the right node where we'll decide for 3. So either we add 3 or we do not add 3. Again here, the terminal condition will hit and this also becomes our answer. We'll continue on the right. We take a decision of either adding 4 or we do not add 4. Intermediary result is complete. The length of current is equal to 2. So we have an answer. Our terminal will hit and return. We make a similar choice elsewhere on the right side of the tree as well. So for the right side, starting from 2 here, we take a decision for 3. Either we add 3 or we do not add 3, where this becomes our answer again because it has already reached the length of k. We take a choice for 4, add 4, do not add 4. On this side of the tree, we do the same. Either we add 3, so 3 gets added in our intermediary result, or we do not add 3. Here, we add 4, or we do not add 4. So this will be empty. We do the same here. Either we add 4, or we do not add 4. This again becomes our terminal case and also our answer, terminal case. You can see we reached the same set of answer which we reached to with our previous 2 approaches. So we have 1, 2, 1, 3, 1, 4, 2, 3, 2, 4. So we have exactly the same result here also. 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. I hope this made sense because this really helps you look at 2 approaches which are a very common pattern in backtracking or recursion type of questions. With that, let's look at the code for approach 2. So looking at the code, let's have a similar function called combos or combinations, where the very first entry that we have is for our candidates. We have our k, and then we have I here. I is the element on which we are making a choice to whether include or exclude it. And then we have our intermediary called current. As we discussed, we'll make 2 calls here. So k remains the same. Either we choose I, where our current will include our ith element, right? And in this case, the candidates will be the same. We pass everything but the element we just made a choice for. So I plus 1 colon, which means I plus 1 gets excluded. Candidates will be passed as it is, because we are keeping this another variable called I, which tracks the element which we are making a choice on. So this is the function call which includes the element I here, and then we make another function call where we exclude it. So that means current will remain as is and nothing gets added. But please notice I will get incremented in both the cases because we cannot use the same element again, and because it's a combination and order doesn't matter. That's why we do this. You will see other questions where depending on the question we do not increment this I in both our calls, but this is one of those questions where we cannot repeat an element and we do increment in both. All right, so with that I think this is what will drive our recursion tree. The last piece which is left is our terminal condition. So we do the same. We say that when length of our current, as soon as it becomes equals to 2, we record the answer. So answer dot append current, and we return. Now if we try to run this code on our example, we can clearly see that there are two calls happening where we make the decision on ith element here, which is 1. So the very call on the left, it'll be called something like this. The candidates will be 1, 2, 3, and 4. And I will become I plus 1, which is 1 here, right? So while it has come to the left, I will become 1 here, and our intermediary current will hold 1. So current will be 1. And on the right also the call will be similar. It's just that the current will be an empty array. If you further go to the left, our candidates will be the same. So I'll shorten this. Let me just clean this a little bit. So here again, our candidates will be the same. I'll just say the candidates via this, or let's just write it down. So our candidates will be the same. Here I will further get incremented to 2 is 2, and our current will be this value right here. When this condition reaches, our terminal condition will hit. It'll record the answer and it'll return. It'll go on the right where 2 will be excluded, and when it goes on the left of taking a decision on 3, we get another answer where again the answer will be recorded in our ANS global variable, and terminal condition will return after recording the answer. You can continue dry running this code on this tree. It'll help you understand the tree and the code. Okay, after that handwritten code, let's formally jump into the code session. Let's look at the code now. This is what the code will look like. Please don't worry about it. This looks a little long because this has both the approaches. So this is the approach 1 that we talked about, and this is approach 2. Approach 1, like we talked of, is about selecting elements for k slots. So you have k slots that you need to fill, and you keep adding elements until you reach k, that is until your length of current becomes equal to k. As soon as that happens, we collect the solution. This is very similar to the code that we wrote by hand. It's very similar to this. Similar terminal condition, similar loop. So this additional condition here where it says that if the candidates become 0, then you have to return. This is not needed if your k is always less than your given candidates, but it might happen that your candidates are less, and in that case you might run out of candidates to add for k, and in that case you just need to return. And this is our recurse function, which goes over and fill all the slots like we looked at earlier. This is our old trick where we select the I candidate and then we pass the rest of the elements over to the next recursive call. So that's approach 1. Similarly, for approach 2, we make choices. So for each position, we say either we want to use I or we do not want to use I. So here current is being passed as is, which means we are not choosing I. I is the pointer on the candidates array that we select. So that's why I is getting incremented here, because no matter if we do not choose the element, we'll always increment the element here, the pointer to our candidates. K remains as is, candidates remains as is. We don't really truncate and pass in this case, we use a pointer instead. The approach is where you choose or not choose. So as we discussed, these two approaches here, they're very important. They show two critical patterns which you can use to solve these kind of questions. You can comment or uncomment the function which you want to see working. I definitely encourage you to go and overlap this code, this textual written code, with the handwritten code we just discussed. Also try and run a few examples in both approaches and try to create trees for those examples. This code will be available in the Git repository. You can look at the link in the description. Feel free to copy paste and see if this works. With that, let's move on to the E, which is evaluate, of our race paradigm. Here we look at the complexities for both. So let's look at the big O time and space complexity for both the approaches. For approach 1 here, we are choosing k from n elements, that is n choose k. This is a very common combination formula. So we can state the complexity also in a similar way, and this is what becomes our time complexity in the big O notation. For space, we maintain the call stack, and this call stack will at once it will only have k elements, so it will scale with k. So that will be its space complexity. Talking about approach 2, since here also we are creating combinations of size k, the complexity remains the same, nck, and the space here will also be O of k, and that is it. This was a very interesting problem combinations. It allowed us to see two approaches. This video will be a bit long, but I hope it will help you understand and get the basics strong for backtracking. Thank you for watching and see you in the next one.